Yeah, you need to do it on the outside, doing all this stuff.
Yeah, I guess so. Hello, everyone. We're a little late today. Uh, we have a higher temperature here in Buenos Aires. We're at 43.4 degrees centigrade here. We are frying our bottoms, and so it's very hot out there. In fact, there was a what do you call it, an orange warning, especially for old people, like me, saying that watch out, don't go outside if you don't have to because it's very hot out there. Okay, I talked about last week about the fact that in this program, JFG's program in Canada, we're probably going to have a follow up, and the follow up will be probably on three issues. One would be energy, the other one would be time, which we covered last week here with my son Hans, right? And the third one was the famous black hole. That's what we'd like to discuss a little bit about today. And one of the issues that I want to discuss, one of the reasons I want to discuss this is that, if you come to think of it, it's a very popular subject. In fact, my son here was telling me that when they discuss physics with his friends, they always, no matter what, end up with a black
No,
hole.
not end up. It always starts there.
Oh, it starts there. But
Black
I
hole's
think
always the one that starts it.
I thought it always ends there as well.
No, no.
No?
It usually ends in what we're gonna talk about today, which is belief. Belief and no. Those two famous words.
Belief and
Belief and no.
no. You
Like
mean
like
no.
I know you
Oh, I
know.
know, I know. Okay, I
I know
see.
you know. He knows. She
Yeah,
knows.
and the black hole is a very interesting subject only because, from my point of view, because it's one of these fantastic things in mathematical physics. I mean, if the hole doesn't do it, nothing will. If that you don't see anything wrong with a black hole, then either you're not paying attention to physics, or you're very superficial about physics, or you have no idea whatsoever about physics. Because once you get to know what a black hole is, what it does, the magical powers it has, well, then the intelligent person takes a step back and starts wondering about, what it is. And so the issue today is really what I'd like to discuss, or how I would like to start the discussion is, what is a black hole? Is there such a thing, right, as a black hole? Is there such a thing as a standalone object, called a black hole that, I can bring here and show you, or whatever? Is there such a thing out there? And that's the key issue. And what we can start with, just to get the ball rolling here, is the definition. What ideas people have about what a black hole is. And I'm not talking about the common folk out there. I'm talking about what do people believe who are in the guild, who are physicists, mathematical physicists, or as I call them, mathematical abstractists, because they deal with abstractions, right? But what do they think a black hole is? That's the issue. And all the representations, all the references I'm going to put up now, just a quick one, just to get the ball rolling here, are all from official sources, okay? So I'm not going to go over the official sources. I'm just saying, I'm going to put this up there so that you can compare, what they say, what they think a black hole is. And here's the first one. What is a black? And I want you to concentrate on a couple issues. Are we talking about a standalone object like a ball? Is a black hole like, the sun, the star shrinks to the size of a ball with a diameter or volume, an object? Or are we talking about, it coming down to a singularity, a zero-dimensional nothing, no volume,
Location.
no structure, just location, I guess. All mass, no body, no matter. Which of these two are we talking about? And here are the two representations. Here's the first one. Okay. Okay, so this is what these people say. Black hole, a great amount of matter packed into a very small area. A star 10 times more massive than the sun, squeezed into a sphere, approximately the diameter of New York City. Now here they're talking about a black ball, okay? Video feed is a little laggy, but sound is sharp. If you present, leave them for a little while. Okay, we'll do our best here, Martin. Anyways, second one, matter has been squeezed into a tiny space. Black holes can be big or small. Scientists think smallest black holes are as small as just one atom. So they're talking about size, they're talking about smallness, they're talking about a physical object, a black ball, right? Next one, the smallest ones are known as primordial black holes. Scientists believe this type of black hole is as small as a single atom. Black holes are objects of extreme density. Such an object packs 3 times more mass of the sun into city size range.
They're all more than zero dimensions.
So what we're talking about here, look at the words that I've underlined. Radius, small, object, what other ones? Big, small, city size, kilometers, the last one there. Okay, so we're talking about something that has size, right? That's the notion that these people put forward. Now here, you're going to see another version here.
Wait, who are these people?
And these are all official sources, by the way. You have NASA here, etc. I haven't put the references, but believe me, these are all from official sources. And here it says, a black hole is not a tangible object, but a region in space. Okay, this is a region, no longer an object, but a region. It's like saying China is a region of the earth, or the palm is a region of the hand, or a little, I don't know, design is a region of the ball. Okay, so we're talking about region of something else. We're not talking about a standalone object, but something that's related to something else. And here it says, black hole is a region of space that has much mass concentrated in it. So it has a lot of mass, no matter. The concept of a singularity is a mathematical concept. Okay, so we're talking about a singularity. That's what a black hole is. And it's a mathematical concept, not a physical, well, they say concept. It's really not a physical object. That's what we're saying. And one of the conceptual difficulties involved with characterizing space-time singularities is that one seems to land in paradoxes if one thinks of them as things. So according to these people, we're not talking about things. The other people are talking about a black ball, which is a thing. So we're talking about concepts versus objects, okay? And here's, however, general relativity characterizes space-time in terms of a metric on a manifold of points. Okay, so we have this duality, and it's built into the definition of the term black hole. Some people think of it as a ball, standalone object. We can all imagine a black ball, no problem there. And other people think of it as a concept, as being part of something else, for example, in this case, you can say space-time, and you can say that a region of space-time, a region of influence, a zone of influence, an area of influence, that's what they'll call a black hole. All mass, no matter. Okay, here's some depictions. Okay, here's the famous, oh, here, let's put these up there. Here you have different types of black holes. Okay. And what you have here is, the different dimensions of a black hole. Some people think it's got 0 dimensions. Again, we're talking about the concept black hole. It says Leonard showed that the black hole's radius is 0. So we have nothing there, right? And scientists now refer to an object with 0 volume, but all of its mass, as a singularity. Okay, so here we're talking about nothing. Essentially, nothing that is a singularity. The singularity is all mass and 0 radius, 0 volume, nothing there. There are other people who think it's one-dimensional. The singularity is a line in space-time, a one-dimensional object in space-time. If we think just in terms of space, it's 0-dimensional. But in space-time, it is one-dimensional because it exists over a period of time. What are they saying? They're saying if you take a 0-dimensional black hole, singularity, whatever, and you stretch it through time, you get a one-dimensional whatever in space-time, in 4-dimensional space-time. That's what they're saying.
So it's 1 dimension out of 4.
All right.
Not 1 out of 3 as in length, width, and height, but 1 out of 4 as in time, but none of the other ones.
Then they illustrate, okay, a 2-dimensional black hole. You'll see this in many places, right? It's got height and width, right? Okay, no problem there. We have the 3-dimensional black hole, a star 10 times more massive than the sun, squeezed into a sphere. Okay, the singularity was surrounded by a spherical gravitational boundary. And there you have a 3-dimensional, more or less, 3-dimensional black hole pasted onto a 2-dimensional stratum or what is it?
Canvas?
I guess substrate, that's what I want to say. Okay, and then you got these other guys who are the naysayers, and they say, oh no, by the way, we have many dimensions. If r is the length of a vector, the singularity comes when x, y, z are 0. So you can have many dimensions for a point singularity. And then we have the other guys who say it's an illegal question. You can't ask the question how many dimensions, whether it's big or small or whatever. A meaningless question because the space-time geometry is undefined at a singularity. So what have you learned today in college, my dear son? Well, I learned that a black hole is 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, many dimensional, and maybe non-dimensional at all. Mm-hmm. Sounds something you want to pass down to your next generation, kids or whatever?
Yeah, but it's kind of tricky because you have to be sure that these are all being said by the same person, not by different sources.
Yeah, all I'm saying is, first we have different people out there obviously have different notions of what a black hole is. Second, if you ask them how many dimensions does it have, like if you want to know if it's 3-dimensional, you can say, well, I can relate to that. It's like a ball. Okay, we can all deal with that. But then you ask the other guy and say, oh no, by the way, you can't ask that question. It's an illegal question. The other guy says, oh no, by the way, you can ask that question. It's just many dimensional because the singularity has all these rays popping out of it. And then the other guy, the 1-dimensional, the 0-dimensional, the 2-dimensional.
Is that to say that there's no consensus on what a black hole is?
Exactly.
But it's kind of irrelevant the way they use black hole, what it is, because they just, why? Let me ask you, why do we have black holes at all?
We have the black hole because from a mathematical point of view, this is what Schwarzschild, depending on your language, showed or proved or through his paper in 1915. He died in First World War, so he didn't outlive it. Karl Schwarzschild, and he came up and he comes up with this equation, and he says, look, if you take a mass of a star that is 3 times as big as the sun, 3 times as massive as the sun, at least 3 times as massive, right? Could be more, and you keep shrinking and shrinking and shrinking it because of its gravitational attraction to its center, it goes into a runaway mode. It goes into a runaway gravitational mode. And what happens? If you're standing on the surface of that object, there comes a time where even if you have the velocity of light, your flash, and you have the velocity of light, or even, well, you can't beat light, but let's assume you have the exact velocity of light, 300,000 kilometers per second, you cannot leave its surface because the mass attraction, the traction caused by that mass, will not allow you to do that. It's called, the escape velocity.
You don't have sufficient escape velocity
Right.
to escape this runaway
Right.
mass pulling in itself. Because everybody can understand about how the sun's mass essentially crushes its own atoms down to its center, or at least pulls them all to the center. But then they take it that step further and say this is a runaway effect that just keeps pulling and pulling and pulling. But why did this Schwarzschild guy invent black holes?
Well, no, all he's saying, he comes up with an equation.
He just said,
And the
What if?
equation says, if
it's
you
just
use
a what if.
if you use Einstein's relativity equations, and in fact, I think you can even do it with Newton's, if I'm not wrong. I haven't thought about that. But the issue is, if you plug in a mass 3 times bigger than that of the sun, then you enter in a runaway gravitational
Well.
pull towards the center of the object, such that it beats any escape velocity allowed for, like in this case, by either special or general relativity, which is 300,000 kilometers per second.
Essentially
In other
saying,
words, it goes beyond that speed, and you cannot exceed that speed, according to special relativity at least. And since you cannot exceed the speed, you have no escape velocity.
essentially saying if there were an object that were this massive, nothing could escape it.
Exactly.
And if nothing could escape an object that's this massive, it would just keep adding and adding and adding to itself.
Right.
But where does the black hole part come in? We're still
Well,
talking about a ball.
Well, again, no, because the gravitation caused by that object still is crunching matter out of existence, according to them.
See, that one he just pulled out of his.
No, because it converts matter into energy. You have Newton's, Einstein's famous equation, E equals mc squared. The little m is mass. It stands really for matter in their minds. Energy is the light that is being irradiated outwards. And if you convert all that mass, all that matter, right, into energy, you have all this energy being sent out. There's the matter turns into energy, but all you're doing is concentrating the mass at that singularity. In other words, what's happening is you're concentrating ever more mass, crunching matter out of existence, all length, width, and Christ, all length, width,
And Christ goes with it.
all length, width, and height. That's what I meant. You crunch it out of existence, and all you have is just pure mass, right? All mass and no matter. And you keep crunching, so now you have an object that is not made out of anything. It's just pure mass.
Yeah.
And that causes an effect, a mathematical effect, over any object that approaches the event horizon, which is the outer region of influence of a singularity, of a black hole.
But I still don't get that extra step. Because we can all imagine a ball of anything that just keeps pulling more and more gases and whatever rocks and happens to come its way,
Yeah.
pulls it towards the towards the center.
Yeah.
But where does I still don't understand why they take that extra step into crushing matter out of existence?
Because they're saying there was a sun. see if you take a neutron star, which is not quite yet a black hole because it doesn't have as much mass, right? It's not yet there.
It's just thinking about it.
Neutron star means that you crunched all this matter into a smaller ball, right? Released the rest as energy as you went along, right? So you crunched it into a small ball, which we'll call neutron, because everything in there, every atom in there has been converted into a neutron. And so they're saying, by the calculations, what we've done here is just crunch the electron flat against the nose of a proton and converted that whole, that atom, that hydrogen atom, we convert it into a neutron,
Okay.
because it has the same atomic weight a neutron has as an hydrogen atom. And so now you've converted that into a solid neutron, and this star is just made out of neutron. So you are crunching electrons against protons here because the gravity is just so great that it just squeezes by sheer pressure. And we'll get that into a minute, but let's just understand what's happening here. You're crunching matter ever so tightly, and what are you doing? You're really squeezing the hell out of the pure atom, releasing whatever you release as energy,
which doesn't get released.
Well, it does get released.
Assuming it,
up to the point that it has escape velocity.
the black hole's escape velocity.
Correct. And
Once it
you
goes
get
into
to a
black hole
point.
mode.
Once you get into that black hole mode, you cross that boundary.
Now, not even energy.
Now, not even the energy, the light can get out. Well, that's one of the versions. There's another version which is the white hole.
So whatever version explains whatever we're talking about. That's the one.
The other version, just in a nutshell, right? There's two particles near the event horizon. And remember, space is made out of particles, positive particles and negative particles, virtual particles. So
whatever that means.
So the black hole swallows one of the two particles. Let's assume it swallows the negative particle, the negative twin. And the positive twin, for some reason, can leave and reach your eyes. And now you have light made, or whatever, energy made out.
Half energy, sorry. It's half energy.
Made out of just positive stuff that the black hole didn't swallow. So they've gone through all this mathematical mumble jumble just to get that point across. But let me tell you what the real problem is. We haven't gotten to the problem yet.
We haven't. Okay.
Let's now discuss problems. Okay, we'll go into the problem. The problem is the following. This is what I want you to think about. Okay, please pay attention here. Just give me a minute here. I want you to think about this. Okay, so the black hole is all mass. Okay. And all these stars that are close to a black hole, they go around the black hole, they go around this invisible mass. Fine, let's concede that. The black hole also swallows part of its skin. It swallows this gas that surrounds this star, which is, a beleaguered star. It's trying to go around, and this black hole is just eating its skin alive, just ripping all this gas from it. Okay? Keep that in mind. These are the two things by which they say that, there must be a black hole there, right in the center of the orbit of this star that's whirling around very fast around nothing, one. And second, something is eating its skin out, sucking the gas right out of its surface. Let's concede, for the sake of argument, those two verifications, those two observations,
You
right?
mean that they've seen these?
Yeah, okay. So
assuming they've seen stars go around nothing, and stars get gases sucked out of them by nothing.
Right? Let's concede those 2 points. The question is the following. If a black hole is all mass and nothing else, how, please explain the physical mechanism by which mass, the concept mass, rips the skin of a star hundreds of thousands of miles away, and how it compels this star to go around in a circle.
You'd have to talk about gravity.
Yeah, no, but again, we're talking about mass. Mass is a concept. Like saying the weight of an elephant forces the ant to go around itself. That's what we're saying. Okay, fine. We're talking about weight. We're talking about mass. Whatever you want to call it, I don't care. We're talking about a concept. We're saying this mass, the mass of the elephant. We're not talking about the elephant. We're talking about the 2,000 kilograms that it weighs, right? And this weight is compelling somehow the ant to go around itself. And the question, how does weight do it? How does mass do it? By what? Please explain the mechanism.
Or show the mechanism.
Because it's easy to show an equation and say, look, when you have so much mass concentrated in a black hole, this is what happens.
Yeah.
This is a description. I want an explanation. I want an explanation of the physical mechanism of how mass compels a star to go around itself. That's what I want. I want a mechanism. And that's what you'll never see. And that's the question you have to ask the mathematician who says, the black hole, the magical black, we pray to it every morning, Fine. Tell me the mechanism. How does mass compel a star to go around itself? How does mass chew gas from a star? That's what I want you to tell me. Anyone who can tell me the mechanism, I'll buy him a beer, for sure.
But that's not a question about black holes. That's a question about gravity first.
Okay,
I mean,
fine.
obviously, you'd need gravity as a prerequisite to the conversation of black holes.
Yeah, but gravity is done with mass because there's no way
Yeah,
they
yeah,
can talk
yeah.
about gravity without introducing the concept of mass.
But I mean, the fact that they use this invisible, not there object, if you can call it an object, or a region of another object, space, whatever you want to, whatever version you want to use. The reason they have black holes, at least to my understanding, the reason they're still around or they're still used in theories is because they've observed planets go around nothing, or planets get knocked out of their orbit or shifted out of orbit,
Yeah.
or just a little bit, maybe by a fraction, and they have to explain these things. They see planets that don't match the orbit they're supposed to, or maybe they have seen gases swirl around nothing, and they have to explain these things. So what
Well,
they
we
do
had the
is they
case of
take
Mercury.
this.
We had the case of Mercury where, because of its eccentric orbit close to the sun, they thought for many years that there was a 10th planet right there, between Mercury and the sun. And they were looking for this planet all throughout the 19th century, like 50 years they were looking for this planet. And simply because they were trying to explain the orbit of Mercury.
Yeah,
And
there's one missing.
Yeah, and it was inexistent. They never found it, and there is no planet there. It was later on, with Einstein's equation that they were able to describe the orbit of Mercury much better, or better than Newton's, right, by a small amount, and they didn't need this extra planet in there. Okay.
But it comes down to this failure of the imagination, where
Yeah.
they say,
Sure.
okay, the gases get sucked out of this planet, or this planet's going around nothing.
Uh-huh.
They go straight to black holes. They
Right.
just kind of say, well, the only
Explanation.
not only
What else
the
could it
only
be?
explanation, but the only mechanism that we've seen that matches
Right.
this is, I mean, the only thing we have for celestial objects are other celestial objects influencing each other. If you have moon going around the sun, Earth going around the sun, you have things going around each other. So there's always a thing that this thing has to go around. There's something, swirling it around, kind of thing.
But it's always a visible thing.
Yeah.
And people see,
So they
when
just
they
make it
discovered
invisible.
when they discovered Uranus, when they discovered Neptune, they discovered it by the effects that these massive planets, had on other objects. They said, "Oh, hold it! This guy is coming out of its orbit. There must be some other object out there pulling on it." And effectively, when they figured out, they did the calculation and said, "Oh, here, look, we found Neptune." Leverrier found that in the 19th century. He found it simply by calculations. And that gave the mathematicians so much power because they said, look, we can predict the existence of an object, and we can predict how much mass it has, how far away it is, how big it is, etc. Because it has to pull so much on this other object. In the case of Uranus, etc., one had an influence over the other. And so they said there must be another planet there. When they put their telescopes in the region, effectively they found Neptune. And so this gave them a lot of power. And the issue today is that we're no longer using the telescope. Now we're using just calculation. We're saying there's a mass there.
Yeah.
We're not saying there's a planet there.
But why?
A star. We're just saying there's a
Why?
mass there.
Because it's the only mechanism
That they can imagine.
that we have observed. It's the only mechanism that we use for celestial objects. Something is spinning this thing around. There's something there, whether we can see it or not. Something's there. That's the only thing that we have to explain it.
Yeah. And so why don't we give an alternative version? I mean, something you can sink your teeth into, And first let's show some pictures, some pretty pictures of some of these black holes, so that and how they operate or how they're detecting these things, so that you can get an idea of what a black hole is. Okay, these are the notions that people have of black hole. Here's a moving region, no longer a black hole. Keep in mind, this is Bugs Bunny's hole that is moving along the ground. Okay, here it is. Now, isn't that beautiful? There's nothing there. We're talking about a hole in a flat, two-dimensional surface, and this hole somehow goes deep in there. I mean, remember, space supposedly is three-dimensional. Here, it's a two-dimensional representation of space, and the hole is going through that two-dimensional space. Now it's a beautiful picture, no doubt about it. So is this a black hole, just a moving hole? Bugs Bunny's hole's moving out of his way. Is that what it is? Okay, that's one version. Here's another one. Here's two black holes colliding. We've had this recently proven that black holes collide. This means this black hole is going to be three-dimensional, both of these. Here you go. Oh, wham! See, they smash each other, right? And they convert into a single black hole. So they kind of influence each other until they form one.
Wait a minute, but they go past each other.
Well, they go past each other because because they're coming from they're speeding against each
Yeah,
other.
but they'd have to
So
be
they
speeding
kinda-
faster than the speed of light.
Yeah, kind of like.
No, seriously.
Yeah, I know.
They would have to go faster than the speed of light to go past each
Well,
other.
again, remember this is a representation by someone who tried to imitate that. Probably if the mathematicians would do it, he would honor your request and say, no, they just collide once and they turn into one. Okay, fine. But the point is, here they're thinking of a black hole as a three-dimensional object that is colliding against another one, can influence the other one, and we're really not talking about mass. We're talking about like two suns.
It looks like two vacuums.
Yeah, I mean, who knows what that is? Anyways, these are the ideas people have. Here's a black hole sucking gas from the surface of a star. Okay, so here's the black hole, how it swallows it in. Here you have a star in there, and the black hole just swallows all that gas from
Yeah,
it.
see, that looks cool.
Yeah, and again, this is what they say the black hole is. And you can see they just make it visible momentarily so you can see what's swallowing that gas. It just goes into nowhere. If you were staring at this black hole from the Earth with a telescope, you would not see that white, that shiny little hole there. That tornado or whatever that is.
Why do they say
toilet
Yeah.
flush?
Why do they say that there's a black hole in the center of every galaxy?
Well, again, because they have no other explanation for the behavior of of a galaxy.
Having the shape that it
Yeah.
does?
See, one of the issues you got to keep in mind is what they've shown, and they cannot explain. They just say it's so weird, that it turns out that the mass of the black hole in the center of every galaxy is related to the number of stars that form the galaxy. Big galaxy, big black hole. Small galaxy, small black hole. And there's a relationship. They made this curve, and they said, look, when we look at all these galaxies, the region in the center has nothing in there. It's like a wide region. We think there's a big black hole there, and this one has lots of stars. And when we go and see this other galaxy, smaller galaxy, doesn't have as many stars. We see the hole in the center is smaller. The region where there are no stars, where there's an emptiness. There's nothing there. And they say, it turns out that the hole seems to have a diameter or the mass of the number proportional to the number of stars in the galaxy.
Wait, so they're saying that the diameter of the hole in the center of every galaxy is proportional
to the diameter of the
diameter
galaxy, essentially, yeah.
So there's a relationship there that must be explained, assuming
Right.
that is what they have observed.
Correct. And this is one of the issues that are being studied even today because they haven't found a solution to that problem. So let's see, I think I have one more. No, that's fine. Let's go into explaining all this stuff with a different mechanism, okay?
Oh, what stuff?
We're going to be explaining what is a black hole, really. Why do stars go around nothing? Why do stars get their gases sucked out of them? Okay, and why, in fact, why there is a relationship between the space or region in the center of a galaxy, which the diameter of that region, which is proportional to the number of stars that are in the galaxy, or proportional to the diameter of the galaxy, whichever way you want to see it. Okay, let's look at a different scenario, okay? And again, you don't have to believe in this. I'm not here to twist your arm. I'm just going to give you an alternative that you can take to the bank. Think about it.
At least have something to compare.
Yeah, you got something to compare it against. And I'm going to show you a different version of what a black hole is, or essentially the phenomenon caused by black holes. That's what I want to show you, okay?
I guess the more accurate way of putting it is the phenomena that have been explained with black holes up until now.
And I'm going to give you an alternative. You don't have to believe in it. I'm just going to give you an alternative. You think of it and, make your own decision. Okay, here's a galaxy, okay? Here's a standard galaxy. And as you can see, the galaxy just rotates there normally, okay? Just think of that, all these stars going around some kind of center. Okay, now as we know, all galaxies have a magnetic field. And that's what I'm going to be using to create my black hole phenomena, okay? But before we can do that, we're saying, if you look at this galaxy, you're saying, why is this galaxy rotating? In other words, why don't the stars just go flying off the galaxy? Why don't they just run away? Especially the stars at the edge of the galaxy.
Gravity.
Yeah, and then the other issue is, why do the stars at the edge of the galaxy travel almost as fast as the ones on the inside? You can see that the galaxy, as you see it here, rotates like a carousel. The buggies on the outside travel just about as fast as the horses on the inside.
Well, they travel faster if you...
Yeah, they travel faster because they cover more distance.
Yeah.
But the question is, why would a galaxy rotate like that? Why don't the stars on the outside travel much slower?
Yeah.
Like Pluto travels around the sun much slower than Mercury. One takes 88 days, that's Mercury, and Pluto takes 243 years to go around the sun. Well, that's so. For how many times does Mercury go around the sun before Pluto goes around the sun once? Well, you'd have to do the calculation. Just divide, 243 years into 88 days, you'll get to your number. The point here is that, that's not how a galaxy rotates. Galaxy rotates with the stars on the outside almost or just as fast or faster than those on the inside. The galaxy rotates as a single platform. Okay? Okay, so that's the first thing you have to explain. Okay, so keep in mind, if you're going to give a solution to these problems, you got to keep these problems in mind.
What are the properties that we have to explain?
Right.
Phenomena.
Right. So that's the property. Now let's look at one thing. What does the rope model say? Well, the rope model says that all stars, we're looking at a galaxy from the top. Okay, like if you you got your eyes on the top of the galaxy.
Or whatever the top is.
Yeah, whatever. You're looking at it from the top, right? Like through the center of the galaxy and all the stars to the side, right? The Earth in this case would be, if this is the Milky Way, would be like 2/3 of the way, somewhere around 2/3 of the way from that center. Okay, now all those bright little yellow lights that you see there, those are stars. And what we're saying is all stars are interconnected. They're interconnected by ropes. That's the proposal. The proposal is that all atoms in the universe are interconnected. One is connected to all others. So all the atoms that comprise a star are interconnected between them, and these stars are interconnected by these enormous coaxials to the star next to it, the closest one to it. And in such a way, all stars are interconnected through and across the galaxy. Now we can put this spider web, as I call it. Let's put this spider web on a galaxy. Let's see what it looks like. Here we're going to place it on top. Okay. So we've got the spider web. We're going to put it on top of the galaxy. We're going to say that all stars are interconnected. Okay. And so they're all twirling like if they were on a platform. Why? Because they're all interconnected. Very simple. They're physically connected. And it's not like a star can leave the galaxy because it's already tied to all other stars in that galaxy and very, very far away from the nearest galaxy.
It's like a spinning disc of yarn.
Right. And
not a ball of yarn, it's a disc of yarn.
It's a disc.
So you can you can kind of imagine that if each one of the pins or whatever, knots, spin, it would take all the other ones with it, and it would act like a carousel.
Yeah, and one important thing to keep in mind here is, first, it prevents the star from flying away. Second, it explains why the galaxy rotates as a whole, as a single disk, or as a single carousel, however you want to think of that, right? Because they are all interconnected. They're tied together like one star to the other, and to the ones on the inside and to the ones on the outside. Every star is connected. Now we can understand why stars don't fly away. At least we have a physical interpretation for it. You don't have to accept the rope model. All I'm saying is, if you look at this with the rope model, you can explain these two features. why stars don't fly away, and why the whole galaxy turns around as a whole, as a disk. Okay, that's the first part. Okay, now let's go for the second part. Every galaxy is verified to have a magnetic field. And here's what we see with a magnetic field inside. If you have a magnetic field in the laboratory, you go to a lab and you can run a magnetic field downwards, and you'll find that a charged ball will circle in that magnetic field. Okay, so now I guess it spins around. It goes in circles like that, like it's showing there, spiraling in that magnetic field. And we can do this experiment in the lab here on Earth, and we've done it many times. We know that that's from electricity. Electricity runs down any cable in a spiraling way. It doesn't go straight from atom to atom like they make you believe many times. It spirals around. Don't take my word for it. Go and research it. Electricity goes around in a spiral from beginning to end in a wire. Okay? And why? Because a charged ball will circle in a magnetic field. As you know, any cable has a magnetic field which has electricity running through it.
And a spiral
right
pattern.
Okay, so now you're getting the idea where I'm going to get my circular movement for a black hole, right there and then, right? So let's look at a magnetic field of a galaxy. Okay, let's go see it. Here's the magnetic field of a galaxy. It looks something like this. Yeah, you gotta make it bigger. Okay, here's a magnetic field. Just think of all those threads coming from those ropes, right? We have the threads themselves forming the magnetic field. They sweep downwards perpendicular to the plane of the galaxy. So if the galaxy is a disk, the magnetic field is much greater than the disk, than the size of the disk, and it's flowing right through the sides of a galaxy and up the middle. Or you can turn it around and say, well, it goes down the middle and down through the sides. Any way you want to look at it. The point here is that this is a magnetic field coming down. That's what we know of a galaxy. We know they have magnetic fields, just like the sun has a magnetic field, just like all stars have a magnetic field. In the same way, a galaxy has a magnetic field, and this magnetic field not only maintains the integrity of the disk, right? It helps maintain the integrity, but it's going to do something else, which I'm going to show next, okay? See what you're seeing there? Now we're going to see what effect it has on a charged object, such as a star. We have a star. Remember, stars do have a magnetic field. And here you have a little white star there. Do you see that somewhere near the center, and it's going around in a little circle very slowly? See that right next to the center, a white little ball that's going around?
I see
this one, yeah, it's the one right there in the center, the big one. There's a big little ball there. I don't know, keep an eye on there and you'll see it go around and around. It's moving.
Number 3, I'd say.
Yeah, there's like 3 little circles there, white circle. The biggest one of those little balls, okay? And you can see that it's moving around and around. Why? Because the magnetic field of the entire galaxy is raining down upon it. And all stars are charged objects. Why does that specific one go around and others don't? Well, because the magnetic field is probably very strong in that region of the galaxy. That's all it is. And so that star somehow gets pushed around. People observe it from the Earth, and they say, oh, look, it's spinning around a black hole. No black hole. It's just the magnetic field sweeping around a charged ball. Just like you saw a minute ago here. Let me show it one more time. Here it is. Just like that. That's what we're saying. Here's a star, and you got the magnetic field of the sun going down. That's why it goes around nothing. That's why they can't see an object at the center of that orbit. Period. You don't need a black hole for that. And all I'm saying is we have an explanation using the rope model, the threads. Okay? The other thing you should keep in mind, again, if it weren't for the rope, all these stars would fly apart. And if it weren't for the rope, all the stars would not travel as a single disk, as a carousel, where the buggies and the horses, the ones on the inside, the ones on the outside, travel at the same speed. Because they're all tied to the same platform.
Well, you lose a lot of things without the rope. You also, the most important one being gravity. You can't really, with a rope, you can
Yeah,
perfectly understand. Okay, you can at least imagine how everything pulls on each other. It's just if all the atoms of me are connected to this thing, then obviously I'm going to be pulling on it. But if you do everything with particles, it gets really weird. We have to be like, well, I guess it's just magic.
let me summarize, okay? Let's see if we get all the main points across, okay? Black hole has never been defined. Some people define it as an object, black ball. Some people define it as a concept, mass, just a region with lots of mass. That's nothing. That's a concept. First, you got to explain how, assuming it's just a bunch of mass, fine. You have to explain the mechanism of how a mass causes any effect by remote control. How does it influence a star that could be light years away? How does it do it? You can't do it with just mass. Mass is a concept. That's a description. You can say, look, if I have more mass, it's going to have this effect. And if it has little mass, it's going to do this. Fine. We can do that. That's a description. I want a mechanism, how mass affects a star far away. We don't have that from mathematical physics. Now, let's go beyond that and say, okay, let's assume that a black hole is a physical object. Okay? It's a ball, some kind. Lots of mass concentrated in a ball. Okay, now we can all more or less sink our teeth into that concept. Still, we have the problem. We have a ball. It's got lots of mass. How does it influence a star far away? We still have the same problem. So whether we have an object or a concept in there, just pure mass or a ball with mass, it doesn't matter. We still have to produce the mechanism, the physical mechanism of how this affects that. Okay? With a rope, we can explain several features of a galaxy. Why? We can explain first how the galaxy maintains its integrity. Why the stars don't fly out of the galaxy. They're all tied together to the center of the galaxy, especially because that's where most of the mass, most of the matter is. And of course, there's a tendency to be drawn to the center. The only thing that gives you that spiral or oval shape is the fact that the galaxy is rotating.
Centrifugal force.
Right. Then you have the invisible magnetic field, which we know is way greater than the diameter of a galaxy. It just exceeds it. And, they've shown one of the reasons they think there are black holes in the center of a galaxy, they've seen these jets. Well, the jets are just the threads that are coming through the center of the galaxy. I mean, we can just as well assume that they're threads and not talk about jets. What we're talking about is the magnetic field sweeping through the center of the galaxy like it would be in a coil. If you take a coil, electromagnetic coil, you'll see that, you'll see the jets coming from the center of the coil, period. We're done. You don't need to go anywhere beyond the lab. And then, what else can I explain? I explain, first, the integrity of a galaxy, why the stars don't fly away, why it rotates as a single carousel.
Yeah.
And then if you add to it the magnetic field, which keeps not only the integrity, helps keep the integrity of galaxy, but also explains why stars move around in circles, because we can see it in the lab here that you can move a charged object like a star in circles if you put it in a magnetic field. What are the magnetic field? Gazillions of threads just sweeping down across, that little star. And I wanted to show today, I just didn't have time to get the little GIF for it, but I have a GIF. I'll show it to you one day. It's more than a promise. I do have it, where a magnetic field eats smoke. You can see smoke just floating around. You turn on this generator, generates a magnetic field. Magnetic field swallows the smoke inwards. And that's exactly what the magnetic field of the galaxy does to the skin of a star that is losing it to nothing. To nothingness. So we have an explanation for these that don't involve the black hole and don't involve the concept mass. If the people want to insist on mass, no problem. Just give me a mechanism for how mass does it. And that's it. And that's the lecture for today.
Well, no, it's not done. Because
we're not done.
I wanted to talk about the belief of black holes. Belief and authority is the part that interests me. Why everyone knows about black holes.
And where did they get the idea?
Yeah.
Where did you hear? Ask this question to yourself. How did you come across the notion of a black hole for the first time? Maybe you can't remember.
There's two questions.
Yeah.
Where did you first hear about it? Which most people don't really know.
Yeah.
But ask yourself that. You might. And the second one is, why do you still believe in them? Would be the second question. I mean, that seems kind of like a weird question because it's like asking, hey, why do you still believe in gravity? But it's like, why do you still believe in black holes is a more specific question because it's not like you deal with black holes every day. So it's not like you have first person experience. No one saw a black hole, no one met a black hole.
It's not like
So
you ever see that.
but it's one of those questions that automatically falls under the realm of either authority, you believe it because someone that you respect told you,
Uh-huh.
or through secondhand experience where some you heard from a friend of a friend of a friend, someone told you or someone told someone else and you overheard it. It's this osmosis of culture where you kind of know about black holes, you kind of have a vague idea, just as everyone does, of what the concept black hole is or means. If you see one in a movie, you can spot it. You can be, they're using black holeage, black holeness. Everyone knows in quotation marks what a black hole
Right,
is.
they don't have to explain to you what a black hole is.
Yeah.
Everybody's
Everyone kind of
familiar
knows,
with it. Yeah.
but it's one of those weird things that it's not something that everyone deals with every day. It's not like a potato. Everyone knows what a potato is. Everyone knows what it tastes like, looks like, smells like, because everyone's seen it, touched it.
Hold it. You want to know what a black hole is? Just go to the toilet, press the button, you'll see what a black hole is. It's just a tornado
but
going down.
it's a different category. It's invisible things that you take on faith. Essentially,
in fact,
it's kind of like God's.
I could assure you, I can almost assure you that you've seen as many black holes in your life as you've seen spirits.
But black holes is in that category of you only believe it because everyone else believes it. Or someone you respect believes it. But
so it's peer pressure.
But it's not peer pressure. It's not like, you're stupid if you don't believe in black holes. Although that's that's very often how it comes across when I deny black holes. It's like, what do you mean you don't believe in black holes? What are you, stupid? It's like you got to defend yourself like you're an atheist among Christians or something. I try not to get in that conversation because because it's a matter of belief. That's the problem. It falls under that category where it falls under the category of, that means all these people are wrong. You're saying Einstein was wrong. You're saying everyone that believes that ever mentioned the word black hole is wrong. All the people that made these movies are wrong, and all deGrasse Tyson, Michio Kaku, all the people
are crazy. Yeah,
all these people are insane. Is that what you're saying? You're smarter than all these people. How arrogant of you! It goes into an ad hominem kind of.
Yeah, but there's an interesting anecdote as a corollary to that, which is that Einstein did not believe in black holes, and he wrote a paper about it. He just didn't accept it, and it turns out he's the creator of the religion. He's the founder of the religion of general relativity in general. And he did not accept black holes. And it's like, Einstein, thanks for what you gave us, but as far as the black hole, we're not even going to mention you. We're not even going to bring you up to, because if people heard that, oh, you mean Einstein didn't believe in black holes? Then they might question and say, oh, hold it. But what you read is always the opposite. They'll say something totally different. They'll say, look, thanks to Einstein's general relativity, we've discovered the black holes, or we now have black holes or whatever. And so people get this idea that Einstein originated or had something to do with a black hole when Einstein specifically railed against the black hole, just like he railed against quantum mechanics. Not everybody is aware of that situation.
Yeah, but
But I mean, if you're going to accept authority, accept the authority of the man himself,
Yeah, the problem with black holes is it falls under the same category as if someone comes and says the Earth is flat. And I don't have any problem with someone saying the Earth is flat.
How flat is flat?
Yeah, that's a different question. But, someone says, flat earther comes, I'm not just going to be like, you're a dumbass. It's like you hear him out first because he might tell you something you don't know, or you might get a different perspective. Yeah. But it falls under that category where it's like they brush you offhand when you say, oh, I don't think black holes are a thing, because there's just so many people that say the contrary, and they've already made movies against it. So it's kind of like it's already part of the culture where you can't deny it, even though no one can show me a picture of it, but again, when you talk like that, you sound like a conspiracy theorist, this crazy guy says, they just believe in what the government tells them, that kind of thing. It's not like that.
You're a crank.
Yeah, it's not like that, but it's like, but it is kind of, there's still something to be said about not having witnessed things firsthand.
Yeah.
it might fall under the conspiracy theorist mentality, but there is something to be said about that. Same thing with the flat earthers, where they say, "I've never seen the Earth, so I can't say for sure."
Right.
Where everything,
And
when
meanwhile, I
someone-
believe it's flat because
where you-
everybody, everywhere I look, it's just flat.
yeah. But it's a problem. It's a problem. But when we talked about that today, it kind of gets you thinking. The deeper question is, how do we come to believe the things that we do believe?
Do we believe by peer pressure? Do
But
we
it's-
believe because it's in our culture already? It's ingrained in our culture.
It's many things.
Do we believe because we go to school, to physics class or whatever, and the teacher tells us this has been proven? The black hole is
what I
pray to the
no,
black hole.
what I came to realize is it really is a matter of age, because you believe you come to believe, the process of believing. We need a word for that. The way you come to believe things, the way you adopt things as belief, is different as a child and as an adult. Because as an adult, you have the power, you have some
Discretionary.
you can question your beliefs. As a child, you just kind of.
I mean, you've already. It's like, I can't learn a language that's overnight like some kid. Little kid, 2-year-old, 3-year-old learns a language just like that.
Okay,
He's got a fresh brain.
That's a different topic
Why?
altogether.
No, but it's
Let's
the
stay
same
on topic.
analogy, isn't it?
No, because we're just talking about how do you come to believe something. As a kid, you just take anything that's spewed at you. I mean, within reason.
Yeah, but I mean,
even
once
Santa Claus.
Once you get it in your brain, it's at the age of 30, 40, it's hard to get that thing out of there because you've been brainwashed.
Yeah, but why? Because you build beliefs on beliefs.
Right.
So if you have to change a belief at 30, now you have to move a lot of things around to adopt a new belief. But that's what I'm saying. As a child, you're just a sponge. It's like they say, kids are sponges. If you act in a certain way, they're going to act in a certain way. If you use certain words, they're going to use certain words. If you have a map of the world like this, they're going to have something pretty similar if you raise them.
Yeah.
But then when they grow up, they fight against the world. They essentially test their beliefs. At least that's what you're supposed to do in university and things like that.
I'm not sure many people challenge
many people don't want to challenge it
Yeah.
because it's just too much of a headache. Yeah. But life will challenge you anyway.
Yeah.
You'll come into situations where your beliefs aren't sufficient. Or that's what learning's for in a way.
Yeah.
So you hit against the world and you say, okay, something has to change here. I don't know what, but it seems like this is the one that keeps causing problems. So let's move that for this, and then you start arranging things.
Yeah.
But this black hole thing is weird because you can't hit anything that makes you question it.
Yeah, because it's taken on
It's
faith.
But why? Because it's completely outside of ordinary day.
Yeah, and you have no way of proving against it. And if the certified expert tells you that it's there and that he's proven it mathematically, who are you to question that?
Yeah, but that's the thing.
It's
entirely. I mean, for us, putting the mathematicians aside and the astronomers aside,
no, astrologers.
They saw it. Assuming there's people that saw them, and assuming there's people that calculated them, we're gonna put them aside. But everyone else takes it kind of. They have no way of questioning these things. I mean, nor do they have the energy or time to talk about them or to consider them. But
is that what it is? No time to research.
But it's like you have nothing to. If I want to know if I'm wrong or right about potatoes, I go and buy one. I can do something. But with the black hole, there's nothing to be done. It's all theoretical.
Well, it's something what I say about theoretical physicists. As an engineer, I had to produce a product. And if my machines didn't run properly, I had a problem. They would shut down my machine until I fixed the problem. So you're not producing product. There's the loss of money. There's a cost. Theoretical physicists, these guys are armchair guys. All they do is they just sit back at their university offices and they play around maybe with the computer. They do some simulations, whatever, and then they come up with theories. Do they lose anything if they get the wrong theory? I mean, if it's black instead of white, will anything change?
Yeah, no one can question them except the next armchair.
There's no loss to anyone who speaks in favor of black holes because so what? What if there is and what if there ain't? Nobody cares. It's it doesn't affect
life.
You still go on with your life. So it's like nobody cares. And first of all, no one understands all that stuff.
If you're wrong about potatoes, you'll find out pretty quickly. If you're wrong about black holes, you'll never find out.
There's no cost. There's no penalty. No penalty. Yeah. Okay, folks. That's it for today, and we'll see you next time. Hopefully, we won't have one this Wednesday. By the way, we'll be out of town. So we'll probably have a transmission on Sunday. So we'll see you then. Same time, same station. Bye-bye.
I guess.